Section 10.2, use combinations and the binomial theorem. So on section 1, or in section 1, we were taking a look at a way of counting up a number of objects out of a group where order mattered, and that was known as a permutation. And today, we're going to take a look at doing a similar thing. We're going to grab a group of distinct objects out of a larger group. And in this case, the order is not important. And in that, we have a combination. So here's a little equation that we can use for our combinations. It looks very similar to our permutation equation. So remember, our permutation, which is represented by an NPR, was n factorial over n minus r factorial. Well, all we've done with a combination is we've used the permutation and we've multiplied it by 1 over r factorial. So there's the difference between the two. And similar, we have n representing a larger group that we pull from, and r are the specific number of objects that we're trying to yank out of that larger group. So let's look at a few examples of this. Here we're going to pick 10 books to read. 5 of them are fiction, 5 of them are nonfiction. And the order in which I pick these books is not important. It doesn't matter which one I start with. So if that's the case, if order is not important, how many sets of 4 books can I read from? So I have in the bucket, we talk about in the barrel, so to speak. We've got in the barrel, we've got fiction and nonfiction books, and there are 10 of them in there. So that becomes our n value, is this 10 number of books. And we're going to reach in and we're going to, how many different ways can we pull out 4 sets of books out of that 10? This becomes a combination where we have n value of 10 and r value of 4, giving us a 10C4, which becomes 10 factorial, 10 minus 4 factorial, and then 4 factorial again. And if I went ahead and put this together, remember factorial is just 10 times 9 all the way down to 1. And if we put this into our calculator, which again, most of your scientific calculators have this ability. And 10C4 would be 210. So we have 210 different ways that I can pull 4 sets of books out. Now, what if we wanted specifically, though, to emphasize a type of book? So what if we wanted a fiction book or a nonfiction book? So in how many groups of 4 books are all the books either fiction or nonfiction? So what we've done here is we've kind of we've given ourselves 2 different categories we have to consider. I want my books to be fiction or nonfiction, and I want 4 of those 5 books to be that particular type. So I want 4 fiction, or I want 4 nonfiction. So the case here is our 2 categories become the type of book, and then 4 of the 5. And a key here is, even though it's not stated in the problem, we're going to have to interpret these as best we can here. This is a situation that we were considering as an AND problem. We're going to get to what this is in a moment. It's called a multiple event, but we have to take into consideration these 2 categories. So what happens is we create 2 combinations. We create one combination for the type of book. So for example, in my barrel I have fiction or nonfiction, and I'm going to pull out of that a fiction book or a nonfiction book. And so this becomes a 2C1. And then we're going to have our 5 5 books that'll be either fiction or nonfiction. And I want to pick 4 of those. So now we have a combination where I've got the 5 books, and I want 4. And what happens with these is we blend these together. And we end up with a 2C1 times a 5C4. And in this case, 2C1 and a 5C4, we have here 2 times 5, for a total of 10 different ways that I can pull the same type of book and have 4 of those 5 in my hand. So this is the introduction to what we call multiple events. We're going to take a look at some more examples of that. We'll get to a more formal definition in just a second. Let's use a standard deck of cards. So we're throwing out the jokers. So 52, we have 4 suits. Each of those suits have 13 cards. And here's an example there on the right-hand side. How many different 5-card hands are possible? So we're going to, again, in my larger bucket here, we've got just 52 cards. And we're going to pull out of that some specifics here. In the first case, we're pulling out 5 of the cards that are red. Now, the 52 cards that we started with, in this case here, we're going to focus on the fact that the cards are red. So we're thinking about the n value and the r value. Again, the n value is the group that we are, so let's go back to the definition. N represents the distinct objects. So in this case, our distinct object, our n, is referring to red cards. So in our bucket, really, are just the red cards. And we're going to pull out of those red cards 5 of them. How many different ways can we do that? So this becomes my R. And so we have how many red cards are there in a suit? There are 26. And we're going to pull 5 of them out, or 26C5, so 26 factorial over 21 factorial times 5 factorial. And we have 65,780 different combinations that I can pull out of that. All right, what if now we want 3 of the cards, so we're still drawing 5 cards, but 3 of them are going to be 8s. Again, you're thinking about the n value, what it represents. It's a distinct representation. So I want 3 of my cards in my hand to be 8s. The other 2 cards can be anything. So again here, we end up with 2 different categories. A category dealing with 8s. And then we have a separate category dealing with other cards. I need 5 of them in my hand. So in the first barrel of 8s, there are 4 8s, and I'm going to pick 3 of them. And in the second barrel, with our remaining cards, which are 48 of them that are not 8s, we're going to pick up 2 more. Give us the total of the 5 cards out of the 52. Now, it might be worth mentioning here, it doesn't again state and, but it's understood. I have to have 3 cards that are 8s, and I need to have 2 more cards. So this really, it is an and problem. We saw one of those back with our fiction, nonfiction books. So it becomes a 4C3, and then we're going to multiply this now by a 48C2. And it might be worth pointing out here that the n values of these 2 categories add up to the 52 total cards in the deck. And the r values add up to the 5 that we need to have in our hand here. So if I did a 4C3 times a 48C2, I'm going to end up with a 4 times a 48C2, 1128, giving me a total of 4,512 ways that I could have 3 cards that are 8s, with the remaining 2 cards being any of the other possibilities. So these are both examples of what we call multiple events. And you can have multiple events that are, as in the case of the last 2 that we saw, an AND situation. And in highlighted yellow here, we see that an AND event means that we're going to multiply those 2 combinations together. But you could also have an OR event. We haven't seen one of these yet. We'll take a look in just a second. Or in this case, we're going to add these 2 combinations together. So AND equals multiply, OR equals add. Okay, take a look at our next one. Your student senate, consisting of a group of seniors, juniors, sophomores, and freshmen, and there are the respective numbers. So we have a total of 18 people in this student senate. And that, again, depending on our question, that could be our larger bucket that we're drawing from, pulling out of 18 people specific groups here. So in our first example, how many different committees of exactly 2 seniors and 2 juniors can be chosen? So here, we're pulling out of just 2 groups, the senior group and the junior group. So we're not going to look at all 18 students. We're going to look at just the groups of seniors and juniors, which would be 6 seniors, 5 juniors. So we have a total of 11 here. So our end value here is going to be 11. Because of the fact that I've got 6 of those and 5 of those. All right, so we want to pick 2 seniors and 2 juniors. And again, we have separate categories working here. So out of the 6 possible seniors, we're going to pick 2. And then here's that word and. Out of the 5 juniors, we're going to pick 2. And in this case, we have a 6C2, which is 15, and then a 5C2, which is 10, giving us a total of 150 ways that I can pull 2 seniors and 2 juniors out of this group. All right, our next question then. How many different committees of at most 4 students can be chosen? All right, at most. Think about what at most means. I could have 4 students, but I don't want to have any more than that. I could also have just 3 students. I could have 2. I could have 1. And we really, there is an option of no students, but that doesn't make sense for us. If we're trying to form a committee, I can't have a committee if I don't have any people on it. So in this case, we have possibilities of 4 or 3 or 2 or 1 is what that means. So 4 or 3 or 2 or 1. So we're talking ORs here. This would mean we're going to add all of these combinations up. Let's start with our, if we had 4 students, that would be, out of the 18 possible, we're going to pick 4 of them. And then we're going to add to that, what if we just chose 3? And then we're going to add to that, what if we chose just 2? And then finally we add to that, what if we chose just our 1 here? All right, and then check in with our different combinations here. So an 18C4 is 3060, and an 18C3 is 816, and an 18C2 is 153, and an 18C1. How many ways can we pick one student? This would be 18. And if we added all that up together, we would get 4,047. Subtracting possibilities is another way of coming up with some of our totals, where if I know my total number of possibilities are, I can pull out of that the ones that I do not want. So in the subtracting possibilities here, we're going to look at them in the case of a binomial situation. You're subtracting possibilities you do not want from the total number of possibilities. So this is just another way you can think about doing these problems that involve phrases such as at least or at most. All right, we'll take a look at it here with this coin example. So we're going to have 3 coins. We're going to toss them and then consider all of the possible ways that those coins could land. So here we have a little visual of our coins, heads and tails. So we have 2 possibilities with each coin. If I went and I tossed them, coin 1, how could it land? And then relative to that, how could coin 2 land? And relative to that, how could coin 3 land? Here are the different ways that all of those coins could end up. And you see here we have 8 ways that we could land these coins. And a way of us thinking about this would be through the use of the subtracting possibility. So we can come up with another look here. Thinking about the visual we just saw, we could also break this thing down into a tree diagram. So the first row here we see would be the options for how coin 1 could land. So our first coin could land on a head, or it could land on a tail. And if our first coin landed on a head, then the second coin could land as a head or a tail. And then the third coin could land head or tail. And again, dependent on our different possibilities, we see we have 1, 2, 3, 4, 5, 6, 7, 8 different ways that these coins could have ended up. So that's a schematic diagram, again, representing could be a head, and from there a second coin could be a head or a tail, and then for each of those 2 coins, a head or a tail option. Again, that's what's giving us our total of 8. Well, if we have coin tosses, every time we toss a coin, we have the possibility of either heads or tails, and then the number of tosses we make would give us the total number of possibilities. So in this case, we had a situation where we had heads or tails, and we were tossing the coin 3 times, and that's what was giving us our 8 total. But now in example 4, we're going to toss 10 different coins. Now because the coins share the same head or tail possibilities, if we follow the same model, we could say that 2 now to the power of 10 gives us a total of 1,024 possibilities for how the coins could end up. How many different ways will at least 4 of the coins, so here we have a phrase at least 4 of the coins show heads. One other way of thinking about this is through the subtraction possibility. And that would be, we have our total number of possibilities, and we remove from that the number of possibilities that we do not want. So if we're looking for heads, that means we do not want to see tails. And if at least 4 of the coins have to show heads, that would mean 3, 2, 1, or 0 coins would have to show tails. So we can subtract from our total the possibilities of landing on tails, and that would look like total minus ways showing tail. So we have our 2 to the 10th, and then now we're going to, all right, how many ways can I show tails? Well, 4, 5, 6, 7, 8, 9, or 10 of them would be heads. That would mean out of the 10, we have 3 of them that could be tails, or there could be 2 of them that could be tails, or there could be 1, or none that are tails. So we're really subtracting this possibility here from 2 to the 10th power. So we have 1024, and then minus 176, and that gave us a total of 848 ways. I could do this also without the use of subtracting by, again, thinking about if I have to have at least 4 heads, that's the minimum number of heads I could have. So that means really I've got, all right, out of the 10 I want 4 heads, or I could have 5 heads, or I could have 6, so on and so on, all the way out to a 10C, 10. And I could add those up and come up with the same number, 848. So I could do a subtraction option, or I could just do a let's count it all up possibility. All right, and then we get into the different component here, using combinations. This is what we call Pascal's Triangle. Blaise Pascal here, a scientist that helped us come up with a bunch of cool things, not just in mathematics world, but also in the science world. So if we arrange our combination values in a triangular pattern, so each row represents some combination value. We have this pattern that develops where we have rows and what we call diagonals. And from that, we can derive what happens, what I would get if I expanded the binomial raised to some power. These numbers that we see here, the numbers in Pascal's Triangle, these guys over here, are used to help me come up with coefficients. So here we see in this first example, written as combinations. So when there are no options that you're choosing from, how can you choose 0 options from 0 in a barrel? There's only one way. That's where that comes from. How many ways can you choose from one option? None of them. And again, that's where that comes from. Or how many ways can you pick 1 from 1? That's where that number comes from. All right, so what's noted here is we have rows based on n values. This is row 0, row 1, row 2, and so on. The n value tells you what row you're in. The second number in Pascal's triangle, so the second combination number, R value, not that guy, the second n number I should say, this could tell you what row that you're, or what diagonal you're in. So the diagonals run this way. That's diagonal 0, that's diagonal 1, diagonal 2, diagonal 3, diagonal 4, and so on. Over on the right-hand side, where we write Pascal's triangle numbers as whole numbers instead of combinations, there is a pattern that from this row 1 down, so from row 2 down, there's a pattern that develops. And the pattern goes like take two numbers of a row and I add them together, I produce another number in the row subsequent to the one you're currently in. So here we are in row number 2. In row number 3, that digit right there would have been a 3. Now, in Pascal, row 0 will always be, diagonal 0 will always be 1. So you'll notice that goes both directions. The outside values of Pascal's triangle are always going to be 1s on the outside. And if I took in, here for example, in row 3, I added 3 and 3, I'd get the 6. And here I am adding 6 and 4, getting the 10. There's the pattern that I'm using to develop each of those numbers within the rows of Pascal's triangle. All right, this helps us develop what we know as the binomial theorem. And what is happening here is we're taking a binomial and we are expanding it. So for example, here we have a plus b to the 4th power. I could take a plus b times a plus b times a plus b times a plus b, FOIL that all out, distribute it, and end up with this expanded form that we see here of 1a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus 1b to the 4th. Or I could use Pascal's triangle to help me get there. So what's important about Pascal's triangle and binomial theorem is that the power tells me what row you are in. Once you are knowing what row you're in, then you use the numbers in Pascal's triangle to begin the process of expansion. So let's try this with some of our examples here. We'll start out with an easy one, and then we'll get to some that are a little more complicated. Let's try it first of all, just identifying numbers in Pascal's triangle, then we'll get to the expansion part. So from a collection of 7 baseball cards, we want to trade 3 using Pascal's triangle to find the number of combinations of 3 cards that we could trade. So we could do our good old generic, I've got a combination here where I have a 7C3, and I know that number is going to be a 35 if I were to put it in there. This is the way it's, again, order doesn't matter here. In looking at Pascal's triangle, here's what we have. Just listing out the numbers within Pascal's world here. Again, adding the 2 numbers above to come up with this number below. And finally, we end up in our 7th row. Here we are in row number 7. All right. In our notation, this is telling us the diagonal 3. Again, this is diagonal 0, diagonal 1, diagonal 2, diagonal 3. So we're looking in that diagonal for row 7. We would end up with a 35. All right, so diagonal 0, diagonal 1, diagonal 2, diagonal. Okay, there's another way if I wanted to use Pascal's triangle. So probably a good idea if we're going to be working with binomial theorems and expansions, take Pascal's triangle, put it on your paper, and then you can use it and refer to it. Here's just a generic layout of binomial theorem at work. And here's what's important to notice about setting up binomial theorem. So we have 2 terms in our binomial, some term A, some term B. Here we get those combination numbers that come from Pascal's triangle. So that would have been like in our row 7, for example, that would have been our 1, 7, 21, 35, 35, 21, 7, and 1. Then what happens is you take each of the terms in the binomial. And when you have the first term, what you do with its power is you start with the power of n, and you decrease by 1 each time you get to a next segment until you get yourself down to a power of 0. Then you do an increase of power for the b's. So in this case, the second term we start with power 0, and then we go up by 1. setup there is how we write the expanded form of some binomial raised to some power of n. So, lead power starts with power of n, decreases by 1. Second term, b, in this case, starts with power of 0, increases from 0 up. So let's try a little bit of this now with some basic binomial expansion first, and then we'll get into one where I've got a 2 coefficient with our x. All right, so here we see, because the power is a 6, I'm talking about row 6. And first thing we'll do is we'll go back and peek at our Pascal triangle row. Here's our row 6, 1, 6, 15, 20. So that's the first thing we're going to look at. And I'm going to give myself plenty of space. So 1, 6, 15, 20, 15, 6, and 1. I gave myself space in between these because I'm going to be filling in the terms from my binomial. So step 1 would be what we just did. Step 1, from Pascal's row n, write out the numbers from Pascal's triangle. That's what we do. Step number 2, and you could split this into 2 steps. I'm going to just blend it all into one. Is start the first term, in this case, the x term, with a power of n, and in this case would be power of 6, and decrease. All right, what would that look like? Well, we have x to the 6th, and x to the 5th, and x to the 4th, and x cubed, x squared, x to the 1st, x to the 0. Now notice I put all those in parentheses. Not so important right now because they're just variables, but had there been a 2x with that, well then that might be something I want to look at with parentheses, and we'll show you that in the second example in just a second. So there we are. Step 2, we started with the first term, and then powers starting with 6 decrease. And then step 3, we break it into a little further. We start the second term of our binomial, which in this case was a y, with power of 0 and increase to the power of n. All right? Second term is y to the 0, and then y to the 1st, and then y squared, 3rd, 4th, 5th, and 6th. Now, pay attention here. You notice the powers of those 2 terms always add up to your n value. They'll always add up to whatever n is, in this case 6. All right, now we're ready to go ahead and take care of this business here. We've got 1 times x to the 6th times y to the 0. Anything to the 0 power we know just becomes 1. So that's going to become 1, and that's going to become 1. And we finally get 1 times x to the 6th. X to the 6th. 6 times x to the 5th. Y. 15 x to the 4th. Y to the 2nd. 20 x to the 3rd. Y to the 3rd. 15 x squared. Y to the 4th. 6 x y to the 5th. And then finally y to the 6th. So this is your binomial expansion of x plus y quantity to the 6th power. All right, let's try this now when you have a term inside your binomial that has a coefficient tagged to it. So in this case, we have 2x minus y to the 4th. Identifying what row we're in. We're talking about row 4. So we're talking about a 1, 4, 6, 4, 1. Just going back here. Looking at row number 4. There it is right there. 1, 4, 6, 4, 1. So in doing our steps, step 1 from row in, write out the numbers that are in that row. So here we go with step 1. 1, 4, 6, 4, 1. Again, leaving myself some space. Now notice in the last attempt, I didn't worry about the sign, whether things are positive or negative. I'm going to let the terms take care of that for me. All right, now in this next example, this is my leading term, 2x. So in step 2, I would take that term, and starting with the power of n, which is actually 4, I decrease. So this would be 2x quantity to the 4th power, 2x quantity to the 3rd power. Now the parentheses become important. 2x squared, 2x to the 1st, 2x to the 0. Then we take our second term within our binomial, which actually is a negative y. And we start with power 0 and we go up. Negative y to the 1st, negative y squared, negative y cubed, finally negative y to the 4th. And again, now we see the importance of putting these things, each of these terms within parentheses. Because each time my power is odd for a negative term, I get a negative expression. And then each time I have a negative with an even power, that becomes a positive value. So now I'm going to see how the signs work themselves out. 2 to the 4th, x to the 4th. We have a power of powers going on right here. So what I end up with is my normal 1, 4, 6. I'm going to just show us step by step. So I end up with 2 to the 4th, which is 16, x to the 4th. And then y to the 0 just becomes 1. And then now we're going to go 2 to the 3rd, x to the 3rd. So this becomes 4 times 2 to the 3rd is 8, x cubed. And then 2 squared x squared becomes 4x squared. And 2 to the 1st, x to the 1st becomes 2x. And 2 to the 0 just becomes 1. Then we get negative y to the 1st, which is just negative y. Negative y squared is y squared. Negative y cubed is negative y cubed. Negative y to the 4th is just y to the 4th. Okay. Now I have, in some cases, negative terms, which means these will become negative. And we go ahead and take care of the simplifying. It's 16x to the 4th minus 4 times 8, or 32x cubed y. And then plus 6 times 4, 24x squared y squared. And then 4 times 2, again, that negative there makes it negative 8x y cubed. And then plus y to the 4th. So there I am with my expanded form of 2x minus y to the 4th power. So notice that the coefficients are different from what Pascal numbers were to begin with, right? We didn't end up with 1s and 4s and 6s and 1s because our first term had a coefficient with it. So if you take it step by step like this, you're going to be okay. And as long as you remember to put parentheses around these terms and remember to put the power on the outside to begin with, and you'll remember that I have to do power powers for some of them. All right. binomial differences. So in that last example, we see this. To expand the power of a binomial difference, where we just had 2x minus y, you can rewrite the binomial as a sum. The resulting expansion will have terms whose signs alternate between plus and minus. If you go back and look at that second example that we just did, we had positive 16x to the fourth, and then we ended up with alternating sign of a negative. Then we went back to a positive, then we went back to a negative, then we went back to a positive. So that's going to be the case if you have a difference of terms there in my binomial. All right, so from the binomial theorem here, each term in the expansion of a binomial raised to a power of n has the form of NCR of a to the n minus r power, b to the r power. This is very helpful for me if I'm going to try and shortcut a little bit, figuring out maybe what coefficients are in terms of certain terms. So in this case, you have this notation, NCR, a to the n minus r, b to the r. Remember that the r value tells you what diagonal you're in. And the n value tells you what row you are in. All right, so let's try this now with this example, 2x minus y to the 7th power. So first of all, I see an n equals 7. Then I'm looking for what is the coefficient in front of x to the 3rd, y to the 4th. All right, I know, because of binomial expansion, that my very first term is going to be an x to the 7th, y to the 0. And my second term is going to be an x to the 6th, y to the 1st, and so on. Decreasing the second term, or first term's power, increasing the second term's power. All right, this is where we're interested. We're interested in what is happening out front there. And, sorry, forgot to include my 2. It's 2x is my first term. And we're trying to find out what is it that's going to be right there. What's going to be after I take into account Pascal number triangle here, and I have this 2 to the 3rd, x to the 3rd thing. I know that's going to be 8x to the 3rd. What am I going to end up with in front of that x to the 3rd, y to the 4th ultimately? That's what this is asking. What's that coefficient that's hanging out there? All right, well, one thing I could do is I could use this notation up here and note that I'm in diagonal 4, of row. Now remember, the sum of the powers tells you what your n is. Well, I also know, because they told me it's a power of 7, and I know I'm in row 7. So now what you can do is just go ahead and take care of this, because we're really only focusing on this component here. I know I get 2 to the 3rd, x to the 3rd, y to the 4th, which is really 8x to the 3rd, y to the 4th. And then there's something from Pascal's triangle that's missing right there. So all we need to do to find this is to go look at the appropriate diagonal and row of Pascal's triangle. So we're going to go look in row 7 at diagonal 4. So I'm going to go backwards here to find our Pascal triangle. Here we are. All right, here's Pascal triangle, row 7. All right, there we are, row 7. Diagonal 0, diagonal 1, diagonal 2, diagonal 3, diagonal 4. So that's the number 35. That should be camping out in front of this 8. So really I have 35 times 8, x cubed, y to the 4th, and 35 question is asking us for this. What is the coefficient that is parked out in front of our x cubed y to the fourth? And that's a quick way to do this without having to actually physically expand 2x minus y to the seventh out. I can just use the locations based off of r and n to figure out what would I multiply, in this case, that